What I want to do in these next couple of videos is to give you an introduction about the process technology, that is the different process steps which are involved in making this microprocessor chip. So in a modern day microprocessor, there are more than 150 steps involved in making and inspecting these different layers. And there are, as you can see, there are 10 plus of these layers involved in going all the way from your transistors, which are on a nanometer scale, and all the way up to your micro bumps, which you use to connect to your PCB, and these are in the micron scale. So we see that there's a three orders change in dimensions going from the transistors all the way up to the microbump, and that approximately translates into these 10 layers that you have. So if you have 10 layers, then you have doubling of your dimensions at each of these layers. That should give you 2 to power 10, or approximately 1000x increase in your dimensions going from your transistors all the way up to the very top level of your interconnect or your microbump. So we want to classify these processes into two broad classes. So we want to classify them as either front end or back end processes. So all the process steps which are involved in making this microprocessor up till the point where you insert a plug. So all the process steps which are involved in making the transistors and making the gate dielectric, doing implants, they are commonly referred as front end processes. And all the process steps involved after that, that is depositing and patterning these metal layers and these interconnects, they are also known as back end process steps. So these are the two broad classes that are used to describe or classify these process steps. And I'm not exactly aware where the origin of this front end and back end came from, but one guess is that traditionally all of these process steps maybe were done in a production line where all the tools were arranged in a conveyor belt kind of a conveyor belt kind of a fashion, and these front end processes, they would start at the very first of this process belt, and that's why they're called as front end. And these back end would be process steps where you do towards the end, so they're called as back end. Another analogy that people give is another reasoning that people give is that these front end processes, they involve things that you etch into the silicon. So these are patterns or etch steps that you do into your silicon substrate. And these back-end process steps, they involve primarily deposition of layers on top of the silicon. So these typically involve growing things on top of silicon. And so that's one reasoning that people give. Another way to classify them is based on thermal budget. So most of your high temperature processes, such as activating your implants, they are done in the front end process steps. So these are the process steps where you can operate at high temperature. Whereas in the back end of the line, you have already made your transistors, so you don't want to damage the transistors which have already made in the front end process. So most of the process steps here, they tend to be done at low temperature or temperatures of less than 400 degrees centigrade. So these are the different ways we can classify the process steps. Let's get started with the front end of the line process flow. So the front end of the line process flow involves many process steps. For the sake of being brief, I want to describe 5 of them to you. The first one is called STI, or shallow trench isolation. This is a process where we dig trenches into the silicon to separate the P transistors from N transistors. And then I want to talk about making the well implants to define the active regions for making these P and N transistors. Then I want to describe to you how to make gate stack, or how to make the gate of the transistor. Then I want to talk to you about how to make the junction, or how to make the source and drain. And then finally, how do we contact, or how do we make contact to our gate and source and drain. So first things first, so the first thing we need to start this process flow is the silicon substrate. So we can either go with this bulk silicon substrate as shown in over here, or we can use this SOI substrate. And this SOI substrate that essentially involves growing insulating layer on top of your silicon. So this is the insulator here, insulator layer, typically silicon oxide. And then this thin layer of silicon is placed on top of this insulator, hence the name SOI, which stands for silicon on insulator. So this silicon layer is now on top of insulator, or other way to look at it, separated from this bulk of the wafer by this insulator. So either way, we can either start with a bulk or a SOI substrate. Some people prefer to use bulk substrates. Some niche application and some other players, they prefer to use SOI as their starting material. So anyway, we can pick either of those, and then the first step that is done is shallow trench isolation, or the first module I should say is the shallow trench, making this shallow trench isolation. And the process flow for that is, first you deposit a layer of nitride, and this nitride layer act as a hard mask. And by hard mask, I mean it's a material which is harder relative to the photoresist material, and it's typically deposited before you deposit your photoresist, and it's essentially a mask for etching, as we'll just describe later. And then the next thing you do is, once you have put this nitride, you cover your wafer with photoresist. And this photoresist itself is consisting of two coatings. So you first have an anti-reflection coating, and then you coat your wafer with photoresist. And the reason why this anti-reflective coating is used is because you want to avoid reflection coming down from the surface of your wafer. So this is depicted in this diagram over here. So if you say if you place your photoresist on top of your wafer, when you shine light, it will reflect back from the surface, and then it reflect back again from the surface, and it will create these standing waves in the resist, which are bad for the fidelity, and they'll lead to essentially feature loss or loss of resolution in your resist. So to avoid that, you place an anti-reflective coating. So you could place this anti-reflective coating either below your resist or on the top of the resist. So when it's placed below the resist, it's called bottom anti-reflective coating, or bark. And then you coat it with the photoresist. So this photoresist is essentially consisting of two materials. One is the anti-reflective coating, and then the actual photoresist. And this is common for all process. So for all process where you do a patterning using a resist, you always use an anti-reflective coating. So I want to define it the first time we are using it. But in any subsequent process flow, when I show you resist and patterning, by default we'll be talking about essentially this bilayer of anti-reflective coating and the photoresist. And then the next step we do after we have our photoresist is we expose it to light. So the part which is exposed that gets developed, and then essentially we remove the part which is undeveloped, or vice versa, depending upon the tone of the photoresist. And what you get is essentially this patterned photoresist. So you pattern your photoresist and you get pattern of your photoresist as shown over here. The next step involved is essentially we etch this pattern into first our nitride, and then use that nitride as the hard mask because it's a harder material as compared to photoresist, to etch that feature into our silicon.